Hi, this is Alex from devstories.eu. Mastering DeepChem, Episode 4 of 15. A neural network cannot digest a chemical structure drawn on a whiteboard. Even if you write that structure out as a text string, standard machine learning algorithms still cannot read it. They need the data pre-chewed into numerical arrays. The bridge between a chemical representation and a mathematical model is feature engineering for molecules. In chemoinformatics, we often represent molecules as smile strings. These are sequences of characters defining atoms and bonds. A carbon ring becomes a specific text pattern. But if you try to hand a raw string to a random forest or a support vector machine, it will fail. A mathematical model requires a fixed-length numerical vector as its input. Transforming that chemical text into an array of numbers is what we call featurization. DeepChem handles this step with a dedicated set of classes called Featurizers. Before looking at how DeepChem does this, there is a common point of confusion to clear up. When people hear about generating a vector representation of text, they immediately think of learned embeddings like those used in modern language models. Chemical fingerprints are not learned embeddings. There are no weights being updated, and no neural networks are involved in creating the feature itself. A fingerprint is a deterministic hashing algorithm. If you process the exact same molecule on two different machines, you will get the exact same array of ones and zeros. The most common featurizer you will use for baseline models in DeepChem is the circular fingerprint. This implements a method known as extended connectivity fingerprints. Here's how the logic flows. The algorithm looks at every heavy atom in your molecule. From each atom, it radiates outward in a circle, looking at the neighboring atoms and bonds up to a specific radius. You can control this radius, but looking 2 bonds away is standard practice. It captures these local structural fragments, runs them through a hash function, and maps them to a specific index in a fixed-length array. The result is a bit vector. A 1 at a specific index means a particular chemical substructure is present. A 0 means it is absent. Imagine you have a list of smile strings representing hundreds of small drug-like molecules. You want to train a random forest model to predict their toxicity. First, you initialize the circular fingerprint class in DeepChem. You configure it to output a size of 1024. This is the part that matters. Every single molecule, regardless of whether it has 10 atoms or 50, will be converted into an array of exactly 1024 bits. You then pass your list of smile strings to the featurize method of this class. The algorithm processes each string independently and returns a 2-dimensional matrix. The rows represent your molecules, and the 1024 columns represent the presence or absence of specific substructures. Because the output is just a standard numerical matrix, you are no longer constrained to chemistry-specific tools. You can hand that matrix directly to standard machine learning libraries. Because fingerprints rely on fixed-length deterministic hashes rather than learned semantics, collisions can happen, meaning 2 different complex structural fragments might occasionally map to the very same bit. Despite this, they remain the fastest, most reliable baseline for turning abstract chemistry into concrete math. That's all for this one. Thanks for listening and keep building.